So how do we operate it? Okay, so the presentation is split into 3 sections. The first section is a short introduction to my work. Sorry?
Can you speak up?
Oh, okay. How about now? Is it better?
Oh. More loudly.
Okay, so short introduction, and then I will talk about parallel random pairing model, which is the original Bolobash model, only its parallelized version. This is equivalent to saying that I will be talking about sampling from the space of multigraphs. And then the third part will be about adapting this model to sampling from more restricted spaces, like simple graph space. Okay, so we already know that we all know what a configuration model is. It was this issue was clarified by Professor van der Hofstadt during his talk, so we don't need to explain it. But that's why in the introduction I would like to shortly explain my motivation for this work. And it's like the motivation came from these 2 publications. The first one is the original ABCD model publication, and the second one was our joint collaboration on the ABCD model, where I proposed a parallelized version of the ABCD model. So usually when you resort to parallelization is because you want more performance, right? So as mentioned by Professor Teberger, the main goal of proposing ABCD model was to be able to generate very large graphs with a community structure with emphasis on performance. And since the original implementation was sequential, the natural way was to extend it into the parallel implementation so that the graphs which are generated are even larger and can be generated faster. So this is what we did together. And the reason I'm showing these 2 references is not only for self-promotion, but I wanted to make a point that, yes, we achieved the goal of speeding up and scaling up the ABCD model in the ABCDE implementation, but I wasn't really very happy with this implementation. This implementation was simply a rework of the original implementation, which was proposed with the original ABCD paper, and well, it is working faster, it is working better, but it has its limitations, and I would like to explain them shortly. So these are the 2 toy examples of the ABCD graphs, and as you know, the ABCD graph is, in essence, it's a union of configuration model or a Chunglu model graphs. So we have the smaller subgraphs which represent communities, and we have what we call a background graph, which connects all the vertices, and this is the noise behind the communities. And the level of this noise is parameterized. So depending on the value of this parameter, the graph will be less or more noisy. But the thing is that from the point of view of performance of generating such a graph, when the value of this mixing parameter is high, of the noise parameter is high, the background graph gets very large. So because it encompasses all the vertices, but it can also have, when it's dense, it has a lot of edges, and it takes a very long time to generate it using the classical method. So the way we approached the parallelization of ABCD was to exploit the fact that the community graphs are independent. So we used the single subgraphs as the units of parallelization. In other words, in order to parallelize a computational task, you need to split it into smaller subtasks and then spread or distribute these tasks onto available processors so that they can be concurrently processed, right? So in our case, the community graphs, the subgraphs, they constitute natural unit of parallelization for ABCD. But there is a problem with the background graph, which is the global graph, right? And it's a single graph. So when this graph gets very large, it actually, its generation can easily dominate the overall time of processing, the overall runtime, and actually it can even cancel out the benefits of parallelization of this algorithm. So our idea was that since this is our bottleneck, generating the global, the background graph, let's try to find a way to parallelize generation of a single configuration model graph, and this is what I was working on. Sorry, no, not this way. So this is just a slide, just to give an idea of what kind of benefits you can expect from parallelization. This is so-called Amdahl's law, and tells you what kind of speed up you can expect by parallelizing your code. So you see that this speed up is capped and so it's not linear. And what's the speed up actually depends on the factor, on the fraction of the sequential code which is left after you parallelize your code, right? So in order, for example, if you manage to parallelize 95 of the overall processing, 95%, you still are capped at around a speed up of 20. So this is something which it's good to have it in mind, and to understand that parallelization, first of all, it's hard, as everyone knows, but then it's not a magic bullet which can solve all the performance problems, right? So this is an example, a toy example of a configuration model graph. No need to introduce it. I will only say that this is coming from the Albert Barabashi book, The Network Science. And since he is using the letter K to denote the sequence of the degrees, I will use it throughout the presentation. Okay, so now I will talk about the random pairing process. So we'll be talking about the space of multigraphs, so the simplest possible case. And as we know, there are two approaches basically to generating configuration model graph. One is the Markov chain Monte Carlo. The other is the original Bolobash random pairing model. So since Markov chain Monte Carlo is an inherently sequential approach, we didn't consider it for the parallelization. We use the so-called direct method of generating the pairing of the vertices, right? So this is basically the very simplistic implementation of the random pairing model. It can be implemented in Julia and Python, probably, right? So
even in Python.
Even in Python. So you see, it's almost trivially simple. So you see, at the input you get your sequence of the degrees. Then you need to do some assertions, like whether it's the sum of degrees is even. We should probably check for the max degree. If you are talking about a simple graph, we should probably check if the sequence is graphical, and so on. Once the assertions, we pass the assertions, what we do next, we generate so-called stubs or the half edges, right? And then what we do with the vector, which I denote by letter H. So letter H represents the vector of half edges, of stubs, and then you permute this vector uniformly at random, and then you obtain your pairing. This is the simplest possible way of obtaining the pairing, where you take the one-dimensional vector H, and you simply take two adjacent elements, and they constitute our vertices. So this is the simplest, probably the simplest possible implementation of this algorithm, and it seems so simple that we shouldn't expect any problems with it. But is this the reality? So this slide explains how these functions here work. So we have our generate stubs function, and we have the shuffle function, which is the random permutation function, right? So they are very simple, right? So this function, what it does, it simply takes at the input, it takes the sequence of the degrees, and it generates our half edges in the ordered manner, right? And then we use the shuffle function, which is a library function in Julia. Oops, I did it. Sorry. So now, what do you do? Control L, right? Okay. So yeah, so this is the library shuffle function, how it works in. It's implemented in Julia, but this is actually this is quite surprising and interesting at the same time, that this is an implementation of the so-called Fisher-Yates shuffle, which is a very old algorithm dating back to 1940s, and it's still in use in the library implementations. So amazingly time-resistant algorithm, right? But the thing about this algorithm is, if you look at it, it looks that it is an inherently sequential algorithm, right? Because in essence, what you do here is it's like a random walk, right, through the space of n factorial permutations, right? So another important fact about these two functions is that if you look at them, they are so simple, you can assess it immediately that their complexity is linear. So the complexity of both these functions is linear in number of input elements, right? So if we go back here for a second, then it seems that our entire random pairing algorithm actually contains of these two steps, which are both linear in complexity. Then, so it means that we should expect this algorithm to work with linear complexity, time complexity, right? Okay, so is it really? So these are the measurements taken for this our simplistic random pairing algorithm, taken for different sizes of the input. So as you can see, let me press the button. Okay, as you can see, for the generate stubs function, the processing time indeed scales linearly with the size of the input, right? So we just multiply the processing time by the factor of 10, and we more or less we can predict the processing time for this algorithm. But for the shuffle algorithm, the library shuffle algorithm in Julia, but something goes wrong, right? So you see that at some point, which is actually at the order of 7, the linearity breaks down, and you no longer scale linearly, but the processing time goes up super linearly. So, okay, sorry. So why is that? So what could be the reason? Well, we may probably guess that maybe the library implementation in Julia is broken, for example, right? But what happened?
Impossible.
Impossible, yes. But it's, yeah, but when you don't know what's the performance bottleneck, it's good to collect some performance statistics, which is what is called profiling. And if we do this exercise for the shuffle function in Julia, we can see the following picture. So this is the execution tree of the shuffle function, or the call graph, if you wish, the call graph. So it shows you how the function works internally and how much time it spends on different tasks. So we can see that for the input in the order of 10 to the 5, right? Most of the time, this function is using the random pseudo-random generator, right? This is the hottest function, which takes the most time. And then we have two other functions which are at the top. This is the get index function and set index function. These are the functions which in Julia are used to read and write an element of the array. So this is read an element of the array, and this is write an element of the array. So you can see that they together, they together consume about 45%, in this case, 45% of the processing time. So these are memory operations. These are the actually communication with the memory, right? So if we go further with our input size, we can see that this picture somehow changes. So first, so you may notice that the get index function or the memory read function is the leader now. So it the sole memory reading consumes 50% of the total processing time. So in case of vector S small, let's say as 1 million elements, and then if you go further, this jumps to even higher values, and it plateaus somewhere at the 90% for the vector of length of 1 billion elements. So why is that? Well, this is because our theoretical model of computational complexity is too simple and doesn't really reflect how the memory operations work in the physical computer. So in case of a physical computer, we deal not with homogeneous memory, but we deal with the memory hierarchy. So we have different types of memory in the computer, and they differ in the access times to the data in these different types of memory. The access time is differ by orders of magnitude, as you can see. So yes, so this graph shows you the cost of the access time to the element of the cell of the memory, or the element of the array, for different working set sizes. And as you can see, you have two cases here. One is the sequential access, and the second is the random access. So what you can see is that the sequential access to memory is more or less linear, but in case of the random access, the access time actually explodes with the size of the input. So because in our implementation we are basically dealing with a very large vectors, so we are hitting this performance wall. Yes. So what you can do about it? Well, the obvious answer would be go west. I mean, try to don't go to the east, go to the west. Try to shrink your working set size. But how can you do it if our intention is to generate very large graphs with millions of vertices and billions, potentially billions of edges, right? So, well, the answer could be divide and conquer, right? This is the usual strategy that you take in parallel programming, is that you need to somehow divide your big task into smaller tasks. And then this chart shows you what happens when you limit your random access to smaller chunks of the array that you, for example, want to shuffle. So this chart, as the previous one, comes from the very insightful paper of Ulrich Draper, which I really recommend to everyone who is interested in programming. It's called "What Every Programmer Should Know About Memory," and it's an excellent, really excellent paper. So you can see that by applying the strategy of chunking or cutting your input into smaller pieces, you can achieve substantial savings in processing time, right? So can we apply the strategy in our case? Well, turns out that yes. And this is a proposition of the shuffle method, which is actually utilizing the strategy of chunking, cutting the input into chunks. So how it works? So this is the so that actually two stages. So it's like a two-stage, two-level shuffle. So the first stage or the first step is partitioning the input randomly, uniformly at random, right? So what we do in this first loop here, lines 1 to 3, is we take our input, the input which we wanted to permute, and we randomly split it into p partitions, right? Once this task is done, we we can then shuffle each partition one by one. This is a very interesting approach, and it was mentioned many times in the literature, I suppose. I personally encountered it in the Mark Newman's networks book. It's mentioned there. This approach is mentioned there in the configuration model chapter. Okay, so you may notice one interesting fact. If you look at this, the second loop, that the partitions which we define by the capital V, so this is our set of partitions, and the small letter V, they represent the partitions. They are disjoint. Since they are disjoint, it means that they can be independently shuffled. This means that this loop could be parallelized because there is no collision in between these partitions, right? So this is our algorithm in the parallel version. What we did here, we simply parallelized the second loop. Now, if we have more than one core or one CPU, it can run much faster because shuffles several partitions concurrently, right? What about the first loop? Can we also try to parallelize it? Where there is no dependency here, that it can happen that if you run it in parallel, then the parallel processes would try to update the same partition. But there is a simple trick, technical trick, which you can apply to avoid this collision, because, well, the standard approach would be to synchronize the work in between parallel threads. But in this case, you can basically kill the performance, because the synchronization, thread intersynchronization is very expensive. So the trick is simply to run this loop twice. The first run is a dry run, where you simply count how many times each thread will hit every partition. And once you know this, you pre-allocate the space in a disjoint manner. You pre-allocate the space in every partition for every thread, and then you run it again. This time you can write the partition collision free. And this runs very fast. It was done in the actual implementation. I'm not explaining it here in the code because it would be a little bit cumbersome to show the algorithm, but this way we can parallelize both loops. And so now we end up with our parallel shuffle algorithm, right? So let's see, is there any improvement in the performance by using this approach? So this is our original shuffle implementation, the library implementation in Julia. This is our partition shuffle. This is the single-threaded Newman's shuffle, the single-threaded version, which runs sequentially, but utilizes the optimized memory pattern by partitioning input first and then shuffling the partitions one by one. So you can see that even in this case, where we only optimize the memory access patterns, basically, so we improve performance for the large input. We improve performance by the factor of 2, for example, in this case. When we combine both effects, the partitioning plus parallel processing, on my modest, humble 4-core i5 CPU, it runs 7 times faster, right? So I think this is a very good result. Unfortunately, it doesn't scale to ad infinitum. So at some point, even with this approach, we hit the wall, the performance wall, which is that since the caches in the CPUs are rather small, at some point if you increase the number of partitions, you will not be able to fit even the smallest possible chunk. So this is the so-called cache line. So you should know that CPUs, they don't read single words from the memory. They read entire lines of words. So it can be 8 or 16 words at once, and this is what they cache. So every partition has to occupy at least one cache line in the CPU, right? So then if you increase the number of the partitions, at some point you will reach the point where you cannot cache these atomic cache lines for every partition in the cache, and then the performance deteriorates, right? Okay. So I'm sorry for, it's more maybe too technical, but okay, we end up with our parallel random pairing algorithm, where we simply, this is the same very simplistic implementation, we simply replace these two functions with our new faster functions. So that's done. But here I would like also to propose another innovation, let's call it, and maybe discuss it with you, because we can obtain additional savings, so performance gains, by applying a different random pairing method, which I called half shuffle. So basically, instead of shuffling the entire vector of half edges, which can be very long, what I would propose is to do it slightly differently. So sample half of this vector uniformly at random, forming partition I, and then the complement of this partition I would be the partition B. So what you get by this is the randomly selected, uniformly at random selected list of elements from list of half edges, and the other half you shuffle it. And my conjecture is that by using this approach, you basically obtain the same number of possible pairings as in the case of full shuffling, but you save a lot of processing time because you shuffle only half of the input, not the entire input. This should be very easy to prove, I think. Right? Okay, so this is another innovation which we probably should discuss, whether it's worth a while. And now, talking about more difficult case, sampling configuration model graph with restricted spaces. So here there are many methods proposed. Professor.
Just quickly summarize what you have in this part, okay?
Okay. So basically, we use this method, right? So we use the pairing with edge switching. It was already mentioned by Bogumi before. And here there are different help. Okay, so maybe I will go just to the final slide. And, so this is the actual implementation, which is currently implemented. Let me see. So it's a little bit more complex, and the reason for that is that we want to produce an adjacency matrix directly from this algorithm, and this algorithm is, in my opinion, doing it in the most optimal way. So this is to avoid sorting, because sorting is also a very costly algorithm, as you know. So if you look on this first algorithm, this is how it's done in the GraphJL library. So you first obtain your random pairing, and then what you do with the random pairing. Actually, this the output that we get from the simplistic algorithm.
Not this way.
Sorry, go west.
Go
So the output that we get from the simple random pairing is hardly useful, because it's just an unsorted heap of edges. And you can't, for example, easily extract a neighborhood of the vertex from this heap of unsorted vertices, right? If this is a very long list, like a billion of vertices, then it will take a very long time. So what you can do, you can sort it, but sorting is also expensive. It's n log n in the best case, right? So you would spend a lot of time on sorting this list, but maybe you can avoid sorting. So this is actually, so what's going on in the GraphGL library is that they build a so-called array of arrays or list of lists, and they iterate the set of random pairs, and they push each element. So in other words, they build a symmetric view of the adjacent matrix. But this is very unoptimal. This is very unoptimal approach because it has a lot of interaction with memory. So for long vectors, it will take a very long time. But you can try it yourself, but yes, but it takes a very long time. This approach here, how would I explain it quickly? So okay, so this is what I wanted to say here. Line number 2 is the same as in the simplistic implementation. We simply generate our ordered list of half edges. Line number 3, instead of shuffling our list of half edges, like in the original implementation, we generate a random permutation of the length W, where this is the number of W is the number of half edges, right? And then this random permutation, it can be interpreted as a special kind of permutation, which is called an involution. So this is a permutation which is entirely composed of 2 cycles, or entirely composed of transpositions. So how can we exploit this fact? Well, this is very simple. It simply tells us swap these 2 elements together and swap these 2 elements together. And by this process, you obtain a transposition of this original vector, and the mapping of these 2 vectors gives you actually the symmetric view of your adjacency matrix, right? So this is the equivalent approach, but it is much faster. And this is the final algorithm. So what's happened here is the same, more or less. So we simply replace this function, which is a sequential library function in Julia. We replace it with our parallel partitioned shuffle algorithm, and we produce in a parallel way. We produce random permutation Z, and then we, let's say, convert this random permutation Z in a involution pi, and then we apply this involution pi in place without copying the vector of half edges. And here we produce a vector of pointers, which tells us where every column of our adjacency matrix starts. And then these 2 together, they compose what is called a columnar sparse, compressed sparse columnar matrix in the terminology of the sparse matrix library. So this algorithm basically gives you the same guarantees of uniformity of sampling, but it does it much faster, and it produces at its output, it produces the adjacency matrix of your configuration model graph. Okay, out of time, right?
Yeah.
Sorry. Okay, so I have some slides about edge switching. We can skip these because you know everything about edge switching and uniformity bias and so on. So we can conclude here. if you are interested in the actual implementation, you will find there. Just please bear in mind that it's quite old. It's like from January. I will update this on next week with some performance tweaks. But the implementation which is there, it works, and you can test it yourself. So thank you very much.